Somewhere in a lab in Palo Alto, a machine just did something that took the world's most powerful supercomputer completely by surprise. It solved a problem in minutes, a problem that would have taken a machine costing hundreds of millions of dollars nearly 1,000,000 years to finish. And right now, companies are pouring $650 billion into building the very technology this breakthrough might be about to leave behind. That's the story you've probably seen floating around lately, wrapped in a headline that promises quantum computing has just made every data center on the planet obsolete. It's a headline built for clicks, and it's built on a real event, but the real event is a lot stranger, a lot more contested, and honestly, a lot more interesting than the headline lets on. So let's slow down and actually walk through what happened. Because the truth here is not a simple story of old technology dying overnight. It's a story about a genuine scientific milestone, a fierce scientific rebuttal, and a multi-billion-dollar industry trying to figure out whether it's building the future or building something that might need a very expensive addition sooner than anyone expected. Before we get into the specifics, it helps to understand why this claim spread so fast in the first place. We're living through a moment where artificial intelligence has become the single biggest story in technology, and the physical infrastructure behind it, the data centers, has become almost as famous as the AI models themselves. Every few weeks, there's a new announcement about a company breaking ground on another massive facility, another multi-billion-dollar deal to secure power and chips, another headline about how much electricity these buildings consume. So when a story comes along suggesting that all of that might be leapfrogged by a completely different technology, one that sips power instead of guzzling it, it taps directly into something people are already anxious about. Is this AI infrastructure boom sustainable? Is it rational? Or is it a bubble waiting for the next big thing to come along and pop it? A headline promising that quantum computing just made data centers obsolete gives people a tidy, dramatic answer to a question that's actually a lot messier and more interesting than any single sentence can capture. Let's start with what actually happened, because this part is not in dispute. In March of 2025, a company called D-Wave Quantum published a paper in the journal Science, one of the most respected and rigorously peer-reviewed scientific journals in the world. D-Wave has been around for years as the pioneer of a specific style of quantum computing called quantum annealing. Unlike the general-purpose quantum computers you might picture from science fiction, annealing machines are built to solve one particular category of problem extremely well: optimization problems, the kind where you're searching for the lowest energy, most efficient state out of an almost incomprehensible number of possibilities. For this experiment, D-Wave's team, working with an international group of physicists and engineers, set out to simulate something called a spin glass. If you're not a physicist, don't worry, this is easier to picture than it sounds. Imagine a three-dimensional grid of tiny magnetic particles, each one pointing in a direction, each one influencing its neighbors. In a spin glass, those interactions are disordered and frustrated, meaning the particles can't all settle into a neat, predictable pattern. Simulating how this system evolves over time, how the magnetic spins shift and interact at the quantum level, is one of the most computationally brutal problems in physics. It matters in the real world too, because understanding these dynamics helps scientists design better superconductors, better materials for electronics, and better components for things like MRI machines. To simulate this, D-Wave used its Advantage 2 prototype, a quantum annealing processor packed with more than 5,000 qubits. And to see how it stacked up against the best classical computer humanity has ever built, they ran the same simulation on Frontier, the supercomputer housed at Oak Ridge National Laboratory in Tennessee. Frontier isn't some outdated machine gathering dust. It is, or at least was, widely considered the most powerful supercomputer on Earth. A machine so large, it fills a space the size of 2 basketball courts and consumes enough electricity to power a small town. Here's where the story gets its jaw-dropping numbers. According to D-Wave's published results, their quantum processor completed the spin glass simulation in a matter of minutes. Frontier, running the equivalent calculation with comparable accuracy, was projected to need something in the neighborhood of 1,000,000 years. And the quantum machine did this using roughly 12 kilowatts of power, which is roughly what 2 average American homes use in a day. Frontier, by comparison, draws enough electricity to light up a small city. When those numbers hit the scientific community, they landed hard. This wasn't just another incremental quantum computing paper buried in an obscure journal. This was published in Science, verified across 11 institutions, and D-Wave called it the world's first demonstration of quantum computational advantage on a problem with genuine, practical, real-world relevance. Not a synthetic party trick designed purely to prove a point, but an actual scientific question that materials researchers care about. For a field that has spent decades promising transformative breakthroughs that always seem to be 5 or 10 years away, this felt, to many people, like the moment quantum computing finally grew up. It's also worth taking a moment to understand quantum annealing itself. because that context makes everything that follows easier to evaluate. Most of the quantum computers you hear about in mainstream coverage, the ones built by companies like IBM or Google, are what's called gate-based quantum computers. They're designed to be general purpose in the same broad sense that your laptop is general purpose, capable in theory of running a wide variety of algorithms, even if in practice they're still limited by noise and error rates. Quantum annealers work differently. Think of an annealing machine as a physical system that naturally settles into its lowest energy configuration. The same way a ball rolled into a bumpy landscape will eventually settle into the lowest valley it can find. D-Wave's machines exploit the strange rules of quantum mechanics, things like superposition and tunneling, to explore that landscape of possibilities in ways a classical computer physically cannot replicate directly. This makes annealers extremely well suited to a specific family of problems, optimization, and certain simulation tasks, but essentially useless for other things, like running the kind of general software you'd find on a laptop, or notably, training the massive neural networks behind modern AI systems. That distinction, general purpose versus highly specialized, is going to matter a lot by the time we get to the data center question, so keep it in mind. Naturally, the internet did what the internet does with any dramatic scientific claim. Headlines exploded. YouTube videos with titles like "Quantum Just Killed AI Data Centers" started racking up views. Bold claims spread across social media, suggesting that the entire foundation of the artificial intelligence boom, the endless construction of massive data centers packed with graphics processing units, was about to be rendered pointless by superior technology that barely sips electricity. It's an intoxicating narrative, especially when you set it against the backdrop of what's actually happening in the data center industry right now, and that backdrop is genuinely staggering. In 2026 alone, roughly $650 billion has been committed globally to building AI data centers. These are not modest facilities. We're talking about sprawling campuses that require their own dedicated power plants, cooling systems that consume millions of gallons of water, and construction timelines measured in years, all in a race to build enough computing capacity to train and run the next generation of artificial intelligence models. Investors, tech giants, and governments are betting an almost unfathomable amount of money on the idea that this infrastructure will remain valuable for decades. So when a headline suggests a quantum computer running on the power of 2 houses just outperformed a facility costing hundreds of millions of dollars, it's easy to see why people started asking uncomfortable questions. Are we about to spend $650 billion on infrastructure that quantum computing will leapfrog before the concrete even finishes curing? Before we answer that, we need to talk about what happened next. Because the D-Wave story did not end with universal celebration in the scientific community. It ended, at least for now, with a serious challenge. Not long after the science paper made waves, a team of physicists connected with the Flatiron Institute set out to test one of the core claims underlying D-Wave's supremacy argument. The idea that no classical computer, no matter how powerful or cleverly programmed, could feasibly replicate what the quantum annealer had done. This is actually the central and most fragile claim in almost every quantum supremacy announcement in history. It's not enough to say your quantum machine is fast. You have to prove that classical machines, even with the best algorithms computer scientists can devise, simply cannot keep up. And history has not been kind to that particular claim. Google made a similar supremacy announcement back in 2019 with its Sycamore processor, and within a few years, classical researchers had developed algorithms that closed much of that gap. The Flatiron researchers took a different mathematical approach than the brute force simulation D-Wave had benchmarked against. Instead of trying to track every possible quantum state directly, which is exactly the kind of approach that explodes in complexity and requires something like 1 million years of computing time, they used a method built around 3-dimensional tensor networks combined with a revived technique from 1982 called belief propagation. Without getting lost in the mathematics, the idea is that this approach finds clever shortcuts, exploiting structure and patterns in the problem that a naive simulation would miss entirely. And according to their results, this classical method was able to reproduce the same spin-glass dynamics that D-Wave's quantum machine had produced, running not on a supercomputer the size of 2 basketball courts, but on hardware modest enough that some reports described comparable results being achievable on something as ordinary as a laptop. If that holds up under further scrutiny, it doesn't mean D-Wave's machine didn't do something impressive. The quantum computer really did solve the problem in minutes using barely any power. But it does mean this specific claim that classical computers were fundamentally incapable of matching it, the claim that gave the story its quantum supremacy label in the first place, is now genuinely contested. Science doesn't settle these debates in a single news cycle. What typically happens is a slow, grinding back and forth, where quantum researchers refine their claims, classical researchers hunt for smarter algorithms, And the true boundary between what only a quantum computer can do and what a sufficiently clever classical algorithm can match keeps shifting. That boundary has moved before, and there's a real possibility it will move again in either direction as both camps keep pushing. So where does that leave the sensational claim that started this whole conversation? The idea that today's data centers are already obsolete? To answer that, it helps to actually talk to the people whose job is building and planning this infrastructure for a living, rather than relying on speculation from a comment section. Industry analysts who track data center real estate and infrastructure investment have been remarkably consistent on this point, and their answer is essentially no, not even close. Andrew Batson, who heads data center research at a major global real estate firm, addressed this exact question directly. When clients ask him whether quantum computing is going to make their existing data center investments obsolete, his answer is straightforward: it does not. Instead, he describes quantum computing as accretive to existing data center infrastructure, meaning it adds to and builds upon what's already there rather than replacing it outright. The real question, in his view, isn't whether quantum computing will replace classical infrastructure, but whether quantum systems will be integrated into existing facilities or require entirely new, purpose-built ones. And based on current trends, it looks like it will be some combination of both. That distinction matters enormously, and it gets to the heart of why the obsolete framing falls apart under scrutiny. Quantum computers, at least the kind that exist today, are not general-purpose replacements for the racks of processors that power your favorite AI chatbot, your video streaming service, or your cloud storage. They are specialized tools, exceptionally good at a narrow category of problems involving optimization, certain kinds of simulation, and specific mathematical structures, like the spin-glass system D-Wave tackled. They are not built to run the kind of massive parallel matrix multiplications that power large language models, the technology behind most of today's generative AI boom. Asking a quantum annealer to train a large language model would be a bit like asking a race car to plow a field. It's an extraordinary piece of engineering, but it's built for a fundamentally different job. There's also the small matter of what it actually takes to run a quantum computer, and this is where the 2 houses worth of power statistic, while true, can be a little misleading if you don't look at the full picture. Quantum computers, like D-Wave's Advantage 2, require extraordinarily specialized environments to function at all. Their qubits are almost unimaginably sensitive to disturbance. Temperature fluctuations, electromagnetic interference, even tiny vibrations from a passing truck can introduce errors into the system. To keep the quantum state stable, these machines have to be cooled to temperatures approaching absolute zero, colder than the vacuum of deep space, using elaborate cryogenic refrigeration systems. They also require heavy electromagnetic shielding to block out noise from the outside world. None of this shows up in a simple 12 kilowatt power figure for the computation itself, but it represents a massive infrastructure investment in its own right, one that looks nothing like a conventional server rack and can't simply be slotted into an existing data center without significant redesign. Analysts at S&P Global, who track the intersection of quantum computing and data center infrastructure closely, describe this integration process as genuinely complex, filled with both opportunity and significant unresolved engineering challenges. Different types of quantum hardware, whether it's D-Wave's annealing approach, the superconducting circuits used by companies like IBM and Google, or the trapped ion systems other companies are betting on, each require their own unique physical environment. There is, at least for now, no universal blueprint for a quantum data center the way there is for a conventional one. That means the facilities being built to house quantum machines over the next several years are likely to remain highly specialized and customized, existing alongside classical data centers rather than swallowing them whole. This is also where it's worth zooming out and remembering just how early we still are in the practical rollout of quantum computing. Fault-tolerant quantum computing, the kind that can automatically detect and correct its own errors in real time without needing a physicist standing by to babysit it, is still described by researchers as something on the horizon rather than something that has arrived. Most quantum systems today remain primarily confined to research labs, university partnerships, and pilot programs run by a handful of hyperscale cloud companies, telecommunications firms, and government agencies. Commercial, mainstream deployment at the scale needed to meaningfully dent global data center demand is something analysts generally place years down the road, not months. Some industry estimates put meaningful commercialization somewhere in the neighborhood of 5 years out. And even that comes with the usual caveat that transformative technologies almost always take longer to reach mass adoption than early enthusiasts predict. None of this means the $650 billion flowing into AI data centers this year is being spent without risk. There are real, legitimate questions about whether some of that infrastructure could become outdated, not necessarily because of quantum computing swooping in to replace it, but because of the much more mundane and immediate risk that faces every major technology build-out, the pace of change within classical computing itself. Chip architectures evolve, Efficiency improves, software gets smarter about squeezing more performance out of existing hardware. Some of today's cutting-edge data centers, built around specific generations of processors, could indeed be surpassed by newer, more efficient classical systems well before quantum computing becomes a mainstream alternative. That's a real and important conversation happening in boardrooms and among investors, but it's a fundamentally different conversation than the one implied by headlines about quantum computers making data centers obsolete overnight. It's also worth remembering that even in the most optimistic vision of quantum computing's future, the technology is expected to complement classical computing rather than replace it entirely. Researchers who study this intersection describe emerging hybrid architectures, systems where classical processors handle the tasks they're already excellent at, like the massive parallel calculations behind AI model training, while quantum processors get called in for specific subroutines where they offer a genuine advantage, like certain optimization problems, cryptographic applications, or material simulations, similar to the spin glass experiment that started this whole conversation. In that vision, the data center of the future doesn't look like today's facilities being torn down and replaced. It looks more like today's facilities gaining a new, highly specialized wing, built to house a small number of exceptionally powerful but narrowly focused quantum machines working alongside thousands of conventional processors. So let's bring this back to the question that kicked everything off. Did a quantum breakthrough just make every data center built today obsolete? Based on everything the actual scientists, the actual industry analysts, and the actual published research tell us, the honest answer is no, not even close, and probably not for a very long time, if ever, in the way that headline implies. What did happen is genuinely remarkable. A quantum computer, using a tiny fraction of the power required by the world's most advanced supercomputer, tackled a scientifically meaningful problem and produced results in minutes that would have otherwise taken an astronomically long time using traditional methods. Now, that's a real achievement, published in one of the most rigorous scientific journals on the planet, and it deserves recognition as a milestone in the decades-long effort to make quantum computing practically useful, rather than purely theoretical. But real science rarely moves in straight lines, and this story is a perfect example of why. Within months of that celebrated announcement, other researchers had already found a classical method that appears to challenge the most dramatic part of the claim, the idea that no ordinary computer could have kept pace. That's not a scandal or a failure. That's exactly how scientific progress is supposed to work. Bold claims get published, other scientists stress test them, and the field inches closer to the truth through exactly this kind of rigorous, sometimes uncomfortable back and forth. It's messier than a viral headline, but it's a lot more honest. Meanwhile, the people actually responsible for planning, funding, and building data center infrastructure are not panicking. They're not pulling money out of AI data centers because a quantum computer solved a spin glass simulation quickly. Instead, they're watching closely, treating quantum computing as an emerging, complementary technology that will likely require its own dedicated, highly specialized facilities over the coming years, facilities that will probably be built alongside, not instead of, the classical data centers going up right now. The $650 billion being poured into this year's AI infrastructure boom is targeting a completely different technological need: the massive parallel processing required to train and run today's artificial intelligence systems, a need that quantum annealing machines, at least in their current form, are not built to address. It's worth pausing here to talk about money too, because the D-Wave story doesn't exist in a vacuum, and neither does the reaction to it. D-Wave is a publicly traded company, and like any publicly traded company, its stock price responds to headlines about breakthroughs. Around the time of the Science publication, the company also reported mixed financial results, including a substantial net loss. That's not unusual for a company operating at the frontier of a capital-intensive technology, and it doesn't undermine the legitimacy of the peer-reviewed science itself. But it's a useful reminder that companies making bold public claims about breakthrough technology often have a direct financial incentive for those claims to be interpreted in the most favorable, most dramatic light possible. That doesn't make the science wrong, but it's worth weighing what independent researchers, without a stock price riding on the outcome, have to say once they've had time to dig in. There's another angle worth exploring, which is what quantum computing might realistically look like as an addition to data center infrastructure over the next decade, rather than as a replacement for it. Picture a large cloud provider's facility 5 or 10 years from now. The vast majority of the floor space is still filled with the kind of hardware you'd recognize today: racks of processors and memory, all handling the everyday workloads of the internet, web hosting, video streaming, and yes, the enormous computational demands of training and running AI models. But tucked into one section of that facility, or perhaps in a separate purpose-built structure nearby, sits a quantum wing. It's a fundamentally different kind of space, heavily shielded, cooled to temperatures colder than outer space, humming with the specialized refrigeration equipment needed to keep a handful of quantum processors stable. Engineers and researchers with highly specialized training work there, running quantum jobs for customers who need help with a narrow slice of problems, designing new materials, optimizing complex logistics networks, modeling financial risk, or running exactly the kind of physics simulation that made headlines this year. That's the picture nearly every serious industry analyst describes when asked about the future of quantum and classical computing together. An addition, not a replacement, growing alongside conventional infrastructure rather than devouring it. This also raises a fair question about timing, because even if you accept that quantum computing will eventually play a meaningful role, the word eventually is doing a lot of work in that sentence. The history of quantum computing is littered with predictions that turned out to be optimistic by years, sometimes by decades. Researchers have been talking about the promise of quantum computing since the 1980s, and practical, widely available quantum advantage on commercially valuable problems has remained perpetually just over the horizon for most of that time. That doesn't mean today's excitement is misplaced. The D-Wave result is a real data point suggesting the field is maturing, but it's worth remembering that the gap between a single impressive laboratory result, published in a single paper, and a technology that reshapes an entire industry's infrastructure spending decisions is usually measured in years of further validation, engineering, and frankly, disappointment along the way before it's measured in months. If there's a lesson buried in this story beyond the specific science, it's probably this. Dramatic technology headlines almost always compress years of nuanced, contested, evolving research into a single sentence designed to grab your attention. And that compression almost always loses something essential in the process. The real story of quantum computing in 2025 and 2026 isn't a story about one technology instantly killing another. It's a story about incremental, hard-won progress, about scientific claims getting tested and sometimes partially walked back, and about an industry cautiously exploring how two very different computing paradigms might eventually work together, rather than in competition. So the next time you see a headline promising that some single breakthrough just rendered an entire industry obsolete overnight, it's worth pausing before you accept it at face value. Ask what the underlying research actually claims, not just what the headline says it claims. Ask whether other scientists have had a chance to respond, to challenge, to replicate, or refute the result. And ask what the people actually building and investing in that industry are saying, because more often than not, the people with real money and real expertise on the line are moving with far more caution and nuance than the loudest voices online would have you believe. Quantum computing is advancing. That much is undeniably true, and the D-Wave result, whatever ultimately happens with the classical rebuttal, represents genuine progress toward a future where quantum machines solve real problems that matter. But the data centers being built today, the ones housing the AI systems millions of people use every single day, are not sitting on borrowed time because of a single spin glass simulation. They're built for a different job, running on a different kind of hardware, solving a different category of problem, and based on everything the evidence currently shows, they're going to be doing that job for a long time to come, quantum computers or not.